everyone. Welcome back to the theory lunch. Today is the last theory lunch of the semester, from what I understand. So we are really thrilled to have one of our greatest speakers, Naama, giving a talk about passing messages while sharing memory. Without further ado.
Thank you, Nika. All right, that was a very flattering introduction. So I'm going to be talking about passing messages while sharing memory. And this is work that I did while on an internship at VMware. And we collaborated with people from all over the place. So Marcos and Irina are from VMware. Rashid is from EPFL. Erez is from the Technion. Sam is from Toronto. And I'm from CMU. Before I get into what I mean by passing messages and sharing memory, I wanted to motivate the work a little bit. So in general, this is going to be a distributed computing talk. So I just wanted to say what distributed computing is so that we're all on the same page. And so in general, distributed computing just talks about when you have multiple processing units or computers that are communicating with each other to calculate something that they want to calculate in common. So a classic example is when you have computers in a data center, and they might be maintaining a replicated database, and so they all have to keep track of the same information, or they might be doing calculations, like small parts of the same very large computation. And another classic example is actually on one computer in an operating system scheduler. You might have many processes and many tasks, and the processes have to coordinate with each other to decide who does which task. And in general, in this talk, I'm going to be focusing on one type of problem that is very common in distributed computing, which is called consensus. And at a very high level, consensus just means agreement. I want all of my processing units, all of them in the network, to agree on a common something. So they all have some opinion of what the truth is, and then they talk to each other, and they have to come to an agreement on what the truth actually is. And this is a very important question. So some applications for it are, for example, if you're maintaining a replicated database, you have to agree with all of the computers that have access to it, like what data was inserted and deleted into your database. And otherwise, you get these annoying database errors. Another example is clock synchronization. If you have many machines and they want to all have the same clock, they might be off from each other by a little bit. And so they have to communicate with each other and agree on what the actual real time is. And lastly, you can think of if you go to some ATM and you do a transaction on your bank account, you would like all ATMs, all points of access into your bank account to agree on what transactions you made. Otherwise, you might get very angry, right? So that's the problem I'm going to be focusing on. But we're going to face a few challenges. And mostly they come from two problems, that the computers on your network might crash, and you might not know about it because they might be slow. So for you, the difference between a slow computer and a crashed computer is very hard to tell. And we're actually going to be talking about the theoretical setting, in which we abstract these two problems as an adversary that can completely control who in my network is crashed and the relative speeds of the processes. And under this setting, we're going to focus on trying to design algorithms that can tolerate as many crashes as possible. So we want them to be robust to the processing units crashing and then not responding. Right, so this is a very high-level idea. And now I'm going to be, you got a sneak peek of all the cool animations. So I'm going to be talking about two models that are very commonly used in distributed computing. The first one is message passing. And that you can think of as the setting where you have many computers that are connected over a network. And in this setting, a computer that wants to send a message picks who the recipient of that message is and simply transfers it across the network. And like I mentioned before, the problems here are that you might have computers crashing. And because of the asynchrony in the network, you might not actually know who crashed. So you can send a message and you don't know whether that message has been received, whether the recipient has actually crashed. Maybe the message is being delayed on the network. You don't know. Now, another very similar model is called shared memory. And in this case, we usually talk about many processes that are on the same machine. And again, you can transfer messages. And this time, you simply, if you have a message, you simply write it on the shared memory, and other people can access and read it. But similar problems happen with crashes. You don't know where they are. And because of the asynchrony, you might not know whether someone has crashed or whether they have read your message or whether they're still calculating their response. Right. So traditionally, these two models have been studied in isolation, even though there are many similarities between them. So a very famous result from '85 says that you cannot actually solve consensus deterministically in a message passing system in which even one process might crash. Right? And then a few years later, Hurley has the same result for shared memory, but two different papers, different context. And yeah.
So when you say you want to achieve consensus, you want everybody who's not crashed to agree.
Yes, exactly. And I'm gonna talk about exactly what I mean a little bit later. But yes, I want everybody who is still active to agree on the same value. Yeah. And that can't be done even if one person crashes. Basically, I can't tell whether that person crashed or was slow, and so that ruins my algorithm. But consensus is too important to just give up and say, oh, there's an impossibility result, so I won't do it. And so in both cases, both in the message passing model and in the shared memory model, there have been results that circumvent the impossibility by either adding randomization to your algorithm or in the message passing case, adding some synchrony assumptions to your network. So it's not completely asynchronous, it might be slow, but you have some bound on the time that it takes for messages to get through. And on the other side, on shared memory, randomization has also been used, and the more common thing is to assume that you have some stronger primitives that allow you access to the memory. So instead of just reading and writing, you might be able to atomically compare and swap or atomically increment some counter, and that helps you achieve consensus. All right. And like I said, they've been studied completely in isolation, which means that they've developed in different directions. So for message passing, most research nowadays deals with Byzantine failures, where a failure doesn't mean that you crash and don't respond. It means that some hacker took over you, and now you're sending evil signals across the network. And in the shared memory, they usually focus on concurrent data structures. So building trees, queues, stacks, whatever it is, in shared memory to allow everybody to access it. But now modern technology actually allows you to use both at the same time. So in modern multiprocessor machines, you can not only communicate through shared memory, but you can also actually send messages between the processes. And even in networks of different machines, technology nowadays actually allows someone from one machine to access the memory of someone on another machine. And so in general, this just means that new technology allows us to use message passing and shared memory together. And so the main question that we want to answer is, well, what would happen if we combine the two models? And so at a first glance, you might think that this is a kind of boring question, because there's actually a result from '95 that claims that these models are equivalent. All right, so really it won't add any power that I have both shared memory and message passing, because they're equivalent. So it looks like there's nothing to do here, right? But if you take a closer look at that equivalence result, you can see that it's actually not quite equivalent. So the result actually says, if I am in a message passing system, I can pretend like I'm in a shared memory system. I can simulate it. So it gives an algorithm that simulates shared memory. and vice versa. So I'm just going to briefly talk about what that algorithm is. So for the message passing to simulate shared memory, the idea is that you want to pretend like you can write and read from a common register. And the idea there is, in order to write, you send your value to everyone with a timestamp, and you wait to hear back from a majority just saying, yes, I heard your message. And then when you read, you again send out a message to everyone saying, hey, I want to read your value, and everyone sends you their most updated timestamp. You wait to hear from a majority, and then you pick the most updated timestamp that you've heard. And this algorithm heavily depends on the fact that you have a majority, so the sets that you heard from when you wrote and the sets that you heard from when you read are the same, or have overlap. Okay? And in the shared memory to message passing, the algorithm is actually simpler. It just says, well, let's just have a huge 2D array, and if P1 wants to send P2 a message, it's going to simply write it in the right spot in the array. And that is all you need to simulate. So the takeaway here is, for the message passing to shared memory, you need a majority of the processes to be participating in your algorithm. Otherwise, you just won't terminate. You'll keep waiting to hear from a majority, and it won't come. Whereas in the shared memory, you don't depend on anyone, right? You can always send a message to whoever you want, and you don't depend on them being alive or anyone else, right? And so, just to make it very clear, when I say participating, I just mean that the processes are not crashed, right? So here I need a majority not crashed, and here I just need one. And in general, this is not a mistake. This majority requirement is actually fundamental. And there's a lower bound showing that you can't solve almost anything, but in particular, you can't solve consensus in message passing if you have less than half of the processes alive, right? So here and for the rest of the talk, I'm going to be using F and N as my notation. F will always mean the maximum amount of failures that are allowed to happen in the system, failures and crashes being the same thing. And N means the number of nodes in total I have in the system. Like we saw before with the simulation result, consensus is the same thing for shared memory, where it can actually solve consensus with only one process being not crashed. All right? Yes?
So now this talk, like, we would be talking about machines that are, say, corrupt, which are like kind of active, but they're sending like incorrect messages?
No, so the idea here is that a crash or a failure means that you got unplugged and you will never respond again. So you're not sending corrupt messages, but you simply don't respond anymore. Okay, so yes?
So in your intro, you mentioned about delays. So we should just ignore, like we'll assume that messages can be sent and received.
So messages, right, so messages are sent and might be very delayed before they are received, but they will be received eventually. So my crashes are not on the message links. Messages don't disappear into thin air. But when they are received by the other end, that person might be crashed, right? And then in that case, they will just never respond.
So, but I mean, is there any, I mean, if I just keep increasing my delay to infinity, in some sense that is sort of like that link has disappeared, or does it?
Yeah. So right. So I mentioned that we have this adversary that controls the timings and the crashes. The adversary can control it and arbitrarily delay a message, but it has to eventually let that message through. So it's not allowed to take it to infinity, but it doesn't have a bound on how long it can delay a message, right? So yeah, and we'll see that when we count time, we don't count the adversary's delay against us because there's nothing we could do about it. So we count like how many messages we sent and things like that. But in general, we're just going to be focusing on what we can tolerate in terms of process crashes. Yes?
You mentioned that you said that something like when a machine crashes, it's crashed forever. So we're not allowing some machine to come back in our system?
Yeah, in this setting, machines don't come back. They just crash and that's it. Yeah. Any other questions? Okay. So now that we hopefully understand the setting, yes?
All right, last question.
Yeah.
For consensus in the shared memory, like what would be an appropriate definition? Like, is it still the same? Like everybody who is active
Yes.
must agree on.
Yeah. So everyone, yeah. And I'll actually get to the formal consensus definition in like 2-3 slides. But yes, the definition is the same. Everyone that still can respond has to agree on the same value. Okay, so now let me briefly summarize our results, and I'll tell you which ones of these I'm going to be talking about. So in general, the first thing that we did in this work is define a model that combines message passing and shared memory. In order to do that, we have a message passing graph on top of which you can pick some shared memory graph. And in this setting, we show that you can tolerate more failures for consensus. You can solve consensus with more than half failures. And how many failures you can tolerate actually is going to depend on your shared memory graph. And we also show a tolerance lower bound that you can't do much better than what our algorithm achieves. And finally, we also discuss a different problem called leader election. Now, leader election is pretty similar to consensus, but instead of agreeing on a general value, people have to agree on one of the processes as the leader and then take instructions from that person. But in this talk, I'm just going to focus on consensus, and I'm going to be showing you these 3 points. All right, so without further ado, we're going to talk about our message and memory model, which we shortened to M&M. And in this model, we always assume you have a fully connected message passing system. And each node has some memory, right? And then on top of this system, we introduce a shared memory graph. And this shared memory graph says if there's a link between U and V, then U can access V's memory and V can access U's memory. So it's an undirected graph, and a link just simply means that these two processes can share memory with each other. All right. Now, the important thing to note is that in real systems, sharing memory with a lot of people ends up making you very slow. And this is because of cache misses that can start occurring and contention hotspots when you have to move around the memory in your system. And so what we're going to focus on is trying to design low-degree shared memory graphs. So we're going to try to increase the tolerance of consensus while keeping our shared memory graph degree low. Yes?
Is the shared memory graph transitively closed?
What do you mean?
If I can access your memory and you can access Stefan's memory, then can I access Stefan's?
No. No. So each person has separate memory, and you can't follow a path. You can only access what you're connected to. Yeah. Yeah. And so in this setting, we're going to focus on how many failures can we tolerate. Right. And so the first algorithm that we might come up with, yeah.
So, I guess in a similar vein,
Yeah.
my first thought would be if the problem with having a lot of shared memory is like caching issues and contention, the thing you would want to minimize would be like the total number of edges or something rather than next, or I don't know why.
Right. So it's actually the contention issues and the cache misses actually happen on each node. So each node maintains its own cache with like some information for who it is that it can share its memory with. And if it has many people that it can share its memory with, then you start having cache misses. Right. So all of these problems are actually per node.
So for like a star, you have like very few edges, but everyone's
Right. So in a star, you have one person who shares its memory with everybody. That person becomes really slow, which means that all of the people who access its memory become very slow. Right. So we don't want stars. Yeah. And so the first idea that we might think of is just to simply connect everybody in shared memory. But I think we talked about this just now, and we know that this is a bad idea because of high degree. But the nice thing about this would be that if we connect everybody in a clique, then we could run any old classic shared memory algorithm, right? So we would bump up our tolerance from n over 2 minus 1 to n minus 1. But like we said, this gives us very high degree, and our main question is, can we do better than this, right? So now this is basically our model. And now we're going to focus on how we solve consensus under this model. So here is the slide that Guru was waiting for. Yes?
So the underlying assumption of the message passing model is that it's a clique?
Yes, for now, for this work, the underlying assumption is that it's a clique, but there's no real reason not to generalize that to it, like any graph. Yeah, so now we finally formally define consensus. And in consensus, what happens is that everyone starts with an input, which is either 0 or 1. And everyone has to give an output, right? So here I have my graph, and everybody has an input. And everybody has to give me an output, which is also either 0 or 1. But it has some constraints. So first of all, like we said, consensus means agreement. So all the processes have to agree on the same value, right? So all of the output values must be the same. But the other constraint is that we have what's called validity, which means that if all of the processes got the same input, then they're not allowed to give any other output, right? So in this case, if all of them had input 0, then this output would not be allowed, and the output would actually have to be 0 as well, right? And our one final constraint on consensus is that we want our algorithm to terminate. Okay. So is everyone clear on this? Yes?
Do you mean every non-crash process?
Yes, I do mean every non-crash process. So if a process crashes, it doesn't need to do anything anymore. It doesn't need to output anything, and I don't count it when I account for termination. Yes?
So when you said a few slides ago that you can't solve consensus deterministically, so what do you mean by deterministically there? What's the non-deterministic?
Right, so actually, the next slide talks about a specific algorithm that does solve it, and I'll show you where the randomization comes in here. So this is an example of an algorithm that solved consensus in message passing. And this is an algorithm that was introduced by Ben Orr in '83 to basically say the impossibility result is stupid. Now, I don't know if you remember on my very early slides, the impossibility results, I had it listed as coming out in '85. Actually, it came out in '83, and in the same year, Ben Orr came up with this algorithm, and the journal version of the impossibility was in '85. So here we're going to be using randomization, but we'll see where that is. So just as a high level, this algorithm proceeds in rounds basically forever until you terminate. And each round is divided into 2 phases, what we call the report phase and the propose phase. And the idea in the report phase is you simply tell everybody what your current value is, right? So you send a message saying report with your value X to everyone. And then you sit and wait to hear back from a majority of the processes telling you what their values are. And then if you hear a majority that all had the same value, then you tell everybody, hey, I heard a majority like this value, which is this line. And then otherwise you say, I'm really confused. I heard many different opinions. I don't know what to do. I'll just send a question mark, right? And then in the propose phase, you wait to hear back from a majority of people who proposed something. And if you heard many people who all agreed on the same value, then you can safely return that value. Otherwise, if you heard like one person who proposed, then you say, okay, well, I'll adopt that value, but I'll keep playing. And then finally, if again you only heard question marks, you're going to flip a coin. And this is the only place where the randomization comes in. You flip a coin to decide what your value for the next round will be. Okay, so a few things to note about this algorithm. First of all, it will terminate, but it might take a while, right? So the thing to notice is that if everyone happens to, on the same round, flip the same coin, then you will terminate in that round. That might take, well, 2 to the n attempt rounds, but eventually you'll get there. And that is definitely if you keep playing forever. And the other thing to note, which is what we're going to focus on, is you're actually sitting there waiting for a majority of the processes, right? So we're going to try to reduce that majority. Okay. So it's okay if you don't quite understand the details of this and why it works. I just wanted to show you what algorithms of this type look like. And this is actually going to be the algorithm that we use as our underlying layer on which we add some like special techniques from the M&M model. Right? So for the M&M model, we want to solve the problem where you have to wait for half the people. And the idea is we're going to use our shared memory edges to communicate with our neighbors. And so every time I send a message, instead of just sending my own current value or proposal value, I'm going to talk to all my neighbors, agree with them on what their values are, and send a list of messages. So for example, here we have our classic network on the left, right. We have our original algorithm with no shared memory edges, and on the right we have on the other side we have the same network but with some shared memory edges. And then we have some nodes that have crashed, right? And so we know that since we need a majority of processes not to crash in the classic version, this algorithm is doomed. Now, the other algorithm, what we're going to do is each live process, each one that didn't crash, is going to say, well, I'm going to simulate my neighbors. So what it's going to do is it's going to write what it thinks P6 should do on P6's memory, and it will write what it thinks P4 will do on P4's memory. And it will actually send a message that's a list of old messages. It's saying, my message is this, P4's message is that, and P6's message is this, right? And so when someone receives this, that someone can pretend like they received 3 messages rather than just 1, right? And so this is how we simulate dead people. And so the main question is, well, how much did we actually gain? How much fault tolerance do we have?
Right.
Yes.
Just a question.
Yeah.
When you kill the machine, you could still access its memory? Like, how did people
Yes.
send something about P6?
Yes. So the idea is that, again, any crashed person will never respond, will never do anything themselves, but the memory is still there and available, right? So you simply write on there. You don't expect them to respond. Right. And so the question is, how much did we gain here? And the answer is going to depend on the shared memory graph. And in particular, it's going to depend on who are the neighbors of the processes that didn't crash. And what we should remember is that the adversary actually chooses who the crashed people are. Right? So for example, we might have this network with 4 crashes. In this case, let's see who's correct. Well, the 2 people who didn't crash, plus their neighbors. So this one is a neighbor as well as this one. And so we actually simulated 4 out of 6. And so we can succeed in our algorithm, right? But if the crashes were a little bit different, so the crash instead of the bottom node was on the other one, then we would have a different amount of simulated nodes. So that one would be correct, but then the new crashed one would crash, and so would its neighbor. And in this case, we simulated exactly half, which is not enough. Yes?
Wouldn't the bottom right one be okay in this example?
Bottom, shoot, yes it would. But pretend it wasn't. Yeah.
This is assuming that the ones that crash all get to write at least one message before they crash?
No, you don't need any assumption like that. So they can crash right from the start, in which case I will impose my input value on them. So I don't know what their input value was because they didn't send anything, they didn't do anything, but I'm going to impose my value on them.
Oh yeah, it doesn't. Right.
Yeah.
The value doesn't matter.
Right. Right. Okay. Okay. So the set of processes that crash actually really matters for how many we can tolerate. And in particular, we want to say, well, for any set of F processes that the adversary picks to crash, the remaining N minus F processes have a lot of neighbors, right? And so there is actually a formal way of expressing this. And this is related to a concept called expansion in graphs. And so this is a very well-studied mathematical object where a graph is said to have an expansion ratio if the following holds. So we look at a subset of the vertices, and we look at its vertex boundary. The vertex boundary simply means that you look at the set and you ask who are its neighbors, and you take out the set itself from it. So you just want to see the neighbors outside of the set. You had a question?
Does this framework require the shared memory graph to also be like regular or something in order to maintain like correctness, to make sure that the thing that they consensus to is actual, like, I mean, what if you had like only one fewer processes receive one input than the other, but the processes that receive the one input are next to a bunch of crash processes and simulate. Maybe I don't know what I'm talking about.
Right, so remember that in consensus, my only constraint is that I'm not allowed to arrive at an output that wasn't anyone's input,
good, cool.
right? But I am allowed to like take a minority, maybe only one person had this input, and I still am allowed to get to that output.
Yeah, thank you.
Yeah. Right, so for expanders, we look at some subset of the vertices in a graph, and we look at the set of its neighbors. And that's going to be our vertex boundary. And then we ask, in my graph, if I look at the ratio between the vertex boundary size and the set size for every possible set, what is the minimum ratio that I get? Right? So what is the worst set that basically has very few neighbors? All right? And in expanders, you actually bound the size of the sets that you consider by half of the graph. Basically, just because if you look at larger sets, then your expansion will also always be tiny, right? If you look at the entire graph, there are no neighbors that are outside of that set, and so it's kind of pointless. And so we can run through a few examples just to kind of understand what expansion means. So in this graph, our expansion would be, well, the set that has minimum neighbors is that one. It has 0 neighbors. So the size of the set is 1. And the size of its boundary is 0, and so the expansion is 0. Now, in a fully connected graph, well, everybody has neighbors, and so the set that minimizes the vertex expansion is the biggest set that is smaller than half, right? So this would be our set, this would be the set of its neighbors, and so the expansion is 1. And then in another case, the worst case scenario here is this set. This is a relatively large set that has relatively few neighbors outside of it. So this is the set of neighbors outside of my orange set, right? And so my expansion is a third. Is everyone clear on that? Okay.
Can you
Yes.
intuitively explain what does the expansion ratio represent? Like if it's high, what does it mean?
Yeah. So generally, expansion relates to how well connected you are, right? So a graph with high expansion is a very well connected graph. And generally, in expanders, another goal that people try to maintain is that you'll have low degree in general, which is why it's very useful for our calls. Okay, so now we can use this concept. And remember that in our case, we want to ask, what is the set of processes that didn't crash, the live processes? We're going to call that set S, and we're going to ask, what is the boundary of S? Right? And that boundary will actually tell us how many more processes we can simulate. Okay, so the adversary gets to pick S. So we want the graph to just simply, all of the sets that the adversary could pick are just really good. And so we have this theorem, and the general takeaway is that if our shared memory graph has good expansion, then we can tolerate many failures. Right? And this theorem formalizes it to give you this expression of the relationship between the number of failures that we can tolerate and the graph expansion H. And this theorem is actually very, very simple. So I'll prove it to you very quickly. The idea is this. We know that the set of live processes is S, and we know that this set has to be larger than n minus f, right? Because the adversary is simply not allowed to crash anymore. We know that the original algorithm has to have at least n over 2 people participating, meaning that the number of processes that we simulate has to be larger than n over 2. Right? And we know that the number of processes we simulate is exactly the set of correct processes plus its boundary. Right? And then we just, and we know that the boundary according to the expansion is simply the size of S, which is at least n minus f, times h, which is the expansion. Right? And from this, we just simply like move things around, do a little bit of arithmetic, and we get to our result. Okay. Yeah.
I just want to interpret this. So if like the graph is a complete graph,
yes,
then h would be 1, right?
Yes.
Then you're saying you can't tolerate any variance.
No, I'm saying I can tolerate, so note that this is times n. So what I'm saying is this is 1 over 2 times 1 plus h, which would be 2, 1 over 4. So I'm saying I can tolerate 3/4 of n.
So it's not a half times 1 plus h, it's 1 over 2.
Yes, sorry.
Oh, I see.
Yeah, right. So this actually says I can tolerate 3/4 of the processes failing, which is actually not quite true. My algorithm can tolerate more, but this is certainly a bound for it. Okay, and so now we've introduced our model and we've introduced how we solve consensus. And then the last part of my talk, I'm just going to give you a taste of a lower bound for the number of failures that we can tolerate. Okay, so before we get into our lower bound, I'm going to show you a classic lower bound that was given by Benor in that same paper, which says the majority requirement for message passing systems is inherent. You can't do better than that. And we're going to prove that by contradiction. We're going to assume that there exists an algorithm that can tolerate more than n over 2 failures, and we're going to show that that algorithm fails. So remember, when we say there exists an algorithm, that algorithm is only in message passing. So it can send any message to any subset of the processes, and it can tell processes to sit there and wait to receive messages. Right. And so we have this graph, we have our algorithm, and we're also going to have an adversary that's going to try to make that algorithm fail. And the adversary will have a very smart strategy, which will be that it will draw a partition in the network. And no one will actually crash, but people on one side of the network will think that the other side is crashed and vice versa. And it's going to do that by simply arbitrarily delaying the messages across the links that are cut. Okay? And so the algorithm, oh yeah, sorry. So we're solving consensus. What the adversary is going to do is it's going to give the same input to one side of the cut and a different input to everyone on the other side of the cut. And so intuitively, if they don't hear from each other, then they're going to have to output different things, and so consensus is broken. And the algorithm is allowed to tell them to send any message to any number of people and to wait to hear back from any number x people. But there's a constraint. X can't be bigger than n minus f, right? Because if the algorithm tells me to sit there waiting for more people than are actually ever going to respond, then I will never terminate, and that's not allowed. Right? So I'm only allowed to wait for n minus f people at most. And note that both sides of this partition are actually bigger than n minus f. So I will be able to wait and just hear people from my side of the partition. Right? And in this case, like I said, the one side will have to output 1, the other side will have to output 0. Once they do output it, then the adversary can let go of that partition and let all the messages through. But then it's too late. Right? So this is the classic lower bound, and it's called the partitioning argument. Okay? All right. So we would like to use the partitioning algorithm, the partitioning argument on our network. But the question is, we know that it has to fail, right? Because we know we can tolerate more than half failures. The question is, where does it fail? Right? And the answer to that is, well, shared memory links are stronger than message passing links. And you can't just simply delay everything across the link. So the idea is the partitioning would still work if there were no shared memory edges across a cut. All right, so if my M&M network looked like this, partitioning would still work just as it did before. All right, but if we had an edge crossing through, maybe an algorithm could use that edge to get around this partitioning, right? But if the two endpoints of that edge were dead, then you couldn't send anything across it. And so the adversary would still win. And so we're going to formalize this intuition into what we call a shared memory cut. And the idea there is that we're going to have a normal cut, but instead of partitioning into two parts, we partition the graph into three. We're going to call them ST and the boundary, B. All right? And so these are our parts. And the constraints are these. There can be edges between S and B and between B and T, but no edges are allowed to be between S and T. Okay? The next constraint is that B has to have two sides. One side that only has links to S, and the other side that only has links to T. And the intuition is that if this is the case, if we have such a cut, then the adversary can simply draw a partition right through the middle of it and crash all of the nodes that are in B. Right? And so this is a cut just of our shared memory graph. And this would be a strategy that allows the adversary to draw a partition.
So why
right?
do you need this extra assumption that SB to like TB1? Like, I mean, even if there was a vertex in B that had an edge to S.
So remember that the memory remains accessible even if a process crashes, so people could still write and communicate on it. But if both endpoints are dead, then you can't. Is that a question?
So is like so what the shared memory represents is separate from the thing that crashing represents. Like shared memory is like a location that all the neighbors of that node can see.
Yes. Yeah. So right. So each node has two sort of parts to it. It has a processing unit and it has memory, right? And those are separate and they can crash separately. Right. Yeah. Okay. Now, what we should note is that there's still a constraint, right? It must hold that the size of S is bigger than n minus f, and so is the size of t. And this is because remember that an algorithm is allowed to tell people to wait for n minus f people, but not more, right? So if S was smaller than n minus f, people in S will sit there and wait until someone from T sends a message to them. Yes?
How realistic is it to assume that all the shared memory writes take the same amount of time? Like, it seems like if you're writing to a shared memory location with some process on, like, the reason that message passing might be slow is because, like, it has to travel through, like, a network or something, and you have to actually communicate with a process that with a machine that might be, like, physically far away or something like that. Why wouldn't you have to still communicate with that to write to a shared memory location that has to live somewhere?
Right. So we don't assume that it takes the same amount of time for every shared memory. Yeah. That it's not. So here's the difference. In a shared memory, communication, when you do a write, you know after you've done your write that it is physically sitting in the memory that you wrote to. So you have this like built-in acknowledgement, sort of. So you know that you've waited long enough for it to happen. Whereas in message passing, you simply send it onto the network, and you don't know what happens to it. And that's the fundamental difference. Okay. Yeah. So again, we're going to be waiting for at least n minus f people. So if one side is actually smaller than n minus f, then we will wait to hear from the other side, and the adversary will have to let that happen eventually. Right? So this argument only works if both sides are smaller than n minus f. And so we have this theorem that says, well, in an M&M network with shared memory graph G, basically you cannot tolerate more failures than exactly what this cut requires you. So what does so basically the adversary is allowed to look for the best cut in the network that that leaves a relatively small n minus s, where s is, without loss of generality, the smaller side of your cut. Okay? So does this make sense to everybody? Now, in the paper, we also relate this cut to the expansion of a graph. But here, I don't have time to do that. So, so I'm just going to finish here and conclude. Right? So in general, I introduced you to the memory and message model, message and memory, the M&M model. And I showed you how to solve consensus on it with better tolerance than just message passing. And then I showed you a lower bound, and I told you that it relates to the expansion. And also in the paper, we talked about leader election, which is very similar to consensus, but has mostly been studied with adding synchrony assumptions to the edges in order to achieve it. And here we show that you need less synchrony assumptions on the edges. Now, there are many, many directions for future work. So the first one is, the first question, I think, would be, well, are these like fancy expander constructions actually practical? Can we actually implement them in like data centers? And the answer is, well, maybe. And in particular, data centers are generally built out of racks of computers that are very close to each other. And it's much easier to share memory inside a rack than outside of it. So you could ask, well, are there constructions that maybe take into account like what the size of your racks is, and try to use that and try to keep your shared memory communication inside a rack. The other model that would be, I guess, the next thing to think about is, I think many people mentioned this, what happens if your memory does crash, right? So when a process stops communicating, its memory becomes inaccessible, right? So there's a lot of study, like a lot of questions that we could study in that framework. And furthermore, we only talked about improving message passing systems using shared memory. You could imagine doing the other way around. You take a shared memory system and you ask, can I improve its performance using message passing? Now, we know that you couldn't possibly improve its fault tolerance, but there are other measurements that you could think about, like the number of I guess, steps that you take. In shared memory, generally, the only way to wait on someone is to actively spin on like reading the place where they're supposed to write to you something to you. With message passing, you don't need to spin, so you might be able to use that time more wisely. And so those are just like a few directions. So that's it. Thanks. Yeah. Yeah.
So this, like, if I'm understanding it right, seems to measure like the optimal like trade-off between like a degree of the graph that you're willing to tolerate and like the fault tolerance that you get out of that. Is there any like nice non-experimental way to actually relate that degree to the speed up that people are going to get from saving on like cache problems or something like that, so that you can like, so that one could actually weigh that against the cost of having more
Right.
faults?
So the question was, can we measure the degree against the speed up that we get from keeping that degree low, right? And the answer is, right now there are no models that allow you to do that. Basically, there are experiments that show that once you get to a degree that's like higher than 20 or so, then you experience a lot of slowdowns. But right now it's all experimental work. But I think it would be an interesting direction to try to formalize what it is that happens and try to talk about that. But I think it also has to do with the size of your cache and like all sorts of parameters like that. Yeah.
Interesting, but really, really hard direction.
Yeah.
Okay.
Yeah. Yeah.
When you have these, when we had shared memory, like it's not the thing we were really making use of is the fact that we could like write and we block until that write is completed and it can't fail because the memory crashes, basically. Is there like a simple thing we could add on to a message passing, like a acknowledgement unit that could be outside the processor and would make message passing as powerful for this sort of thing as shared memory?
So I think the answer is probably. But you would be changing what message passing means, basically. And if you change it, like, you don't have to change it a lot to get to exactly what shared memory means. Right, so in this abstraction, we said shared memory is you go and you write onto someone's memory. And this abstraction is good because in practice, it actually does something different. Right, so if you go and write on someone's memory, you don't interfere with their CPU. Whereas if you send them a message, they do have to react to it. But for the fault tolerance that we're measuring, it is true that you could say, well, if I sit there and like don't do anything else at all until I receive an acknowledgement for my message, then I believe that you do get to very similar semantics as shared memory. Yeah, yeah.
Possibly very related question.
Mm-hmm.
Are there synchrony assumptions that correspond to the extra strength you get from shared memory? Or is there like something that clearly distinguishes the power you get from shared memory versus the power you get from synchrony assumptions?
So I think they all of these assumptions are very related to each other, right? So synchrony versus like atomic primitives versus randomization, they all kind of achieve the same goal. I think the shared memory is a very simple abstraction to work with. The synchrony assumptions that you add to things are very messy, and in general, what happens is you say, well, for example, let's say I know that there is a bound, but I don't know a bound on like the synchrony, but I don't know what it is. I could find it by like doubling the amount of time I wait every time, right? But the shared memory doesn't require you to do that. And in practice, these things actually like correspond to different strategies. So yeah, yeah.
So can you talk about the semantics of message passing and shared memory? So when you say that I'm sending a message, is it like written to a buffer which is read by the receiver, or like when you say there's a shared memory, like is there like a memory data structure which can be accessed, and what does it really mean to write on it? Like when I say I write something on this shared memory, and then I execute some other instructions, what does it mean to execute the other instructions? Does it mean that the thing has been written, like with all the processes that are interacting with each other?
Okay.
Like yeah, it's a little bit unclear, but I'm trying to understand what exactly do you mean when you say I send a message? What exactly do you mean when you
Right.
send a
So
message?
yeah. So right. So the question is basically the exact semantics of sending messages and sharing memory. So yeah. So when we send messages, we assume that basically you can think of the two endpoints, both for sharing memory and sending messages, as people who are doing work. Right. There's a question of how much work is it to send a message, and when do I think I'm finished with my work, and when does the other person recognize that I've done this work, right? So in message passing, we do assume that there's an ordered buffer per link. So when I send many messages on the same link, the recipient will receive them in order. But the work that I do ends when I kind of release my message on the link. And I don't know how long it takes for the message to travel across the link and get to your buffer. Whereas in shared memory, I go and I walk across the link myself, and I write my message on your memory in a place where you can access it later. And so the work that I do encompasses making sure that once I'm done, you can access my information. Does that answer your question? Yep, there's.
What happens if you have Byzantine processes?
Right, so Byzantine are a whole different story. The answer is that in general, the story flips. Shared memory is very bad at handling Byzantine because like a Byzantine process can write anywhere and completely ruin your data, whereas message passing is quite good at handling it, right? You only receive this one message from someone, or maybe a few messages, but from the same person, and you could maybe develop something that recognizes that these are Byzantine. So the story flips, and possibly we could talk about having shared memory handle Byzantine failures using message passing.
What about the network? If you have a message passing system that the network can lose messages, and you have to keep repeating sending to make sure we get them.
Yeah, so also a slight variation on the model. In general, what you said basically is the only solution is you keep sending your messages until until something tells you that you're done, right? Yeah.
I've never heard of this. What's a Byzantine process?
Okay, a Byzantine, so you know how I said that my failures mean that a process crashes and just stops executing and never responds? There could be a different type of failure, which you can think of as a hacker, like a malicious attack, which instead of not responding, that process starts sending wrong messages and trying to make the algorithm fail on purpose. So that's a Byzantine failure.